How's everyone feeling today?
See better days.
Well, I hope that better days come soon. Let's see. That's a lot more emails than I left yesterday. Give me just a second for the basement Wi-Fi to start working. Please. Alright. So, main events coming up in this particular course. Today is Friday, April 12th. And next week, specifically the 15th through the 17th, we'll be having test number 2. Like the last one, it'll take place during lab. So on lab, any one of those 3 days, 1:30 to 4:30, Monday the 15th, Tuesday the 16th, or Wednesday the 17th, you should come to this room and you will take the test then. As with the last one, it will be designed to take you an hour, but you will have up to the full lab time to take it. You can attend any one of those 3 days. There is no lab next week. It says the test is what we are doing. You can come to any one of the 3 days. You don't necessarily have to tell me which one you are attending, because unlike the lab room, there are more chairs in here. So any one of these 3 afternoons you can show up, and lecture next week will be, at least for these 2 lectures, Monday and Wednesday will, as per last time, be review days to make sure that everyone is feeling confident and comfortable before they take the test in the afternoon. Today, I plan on looking over the study materials for the test that I have posted to Brightspace, making sure everyone knows exactly what's going to be on the test. And that'll be mostly it for the day. Depending on how long that takes, I might go over some of the facts about light I want to cover before the end of the semester, but those will not be on test 2. That'll only be if we have extra time today. With all that said, how are you guys feeling? Do you guys have any questions for right now? All right. Let's take a look at Brightspace. Within Brightspace, I've been adding tabs for each chapter as we cover them. The numbers skip around a lot as the numbers are based on the textbook the course is based on. There's a tab specifically for test 2. It is on chapters 8 through 20. Do note that we didn't cover every number between 8 and 20. We skipped around a bit, but if it is a number between 8 and 20, then it'll be on here. 9 and 10 are a little out of order since I talked about those on the day of the eclipse. But basically every tab from the test 1 tab down to the test 2 tab is material that will be here. And as with test 1, doing the homework within each tab is the best thing that you can be doing. Each tab again does have a homework assignment. The tab itself lists what numbers out of the book you should do, or alternatively, there is a document here that just has all the questions written out as well, and a second one with the answers. There's one of those for each chapter, and you should be doing those as the semester goes on. But within the test 2 tab itself, there is a list of all the concepts from the chapters that will be on the test. If it's not on this list, it's not on the test. And also some additional practice questions if you've done all the homework or want something more specifically focused towards the test to direct your attention to. The way that I make these extra questions is I finish the draft for the test so that I know exactly what's on there, and then I write practice questions that use all the same principles in similar ways. So you should be doing the homework throughout the semester, but this is the most direct focused thing you can work on to study for the test. If you can do this comfortably, you'll be fine for the test. We can look over this later as well. I'll be posting answer key to it this afternoon. In reference to the test itself, as with test 1, it has 105 points spread among 13 questions, graded out of 100. So there's bonus points built in. Rather than giving you one bonus question that you may or may not get, there's just more points than you need, and you just do the test to the best of your ability. There are 13 questions on this one, which is technically more questions than on the first one. But because there's a lot of different topics on test 2, what wound up happening is there's more questions, and those questions tend to be shorter since they're about more varied things. Test 1 had a lot of multi-parters on it. I think it was about 9 questions, and most of them had 2 to 3 parts to them. Test 2, there are more questions, but they are shorter. There are more single part questions on test 2 than there were on test 1. So again, the amount of work should be the same, but test 2 has more varied list of types of thing on it. Questions so far? All right. Now, looking at the tab itself to check over this list so that you would hear from me exactly all the things you should know and be able to do before the test. You should consider this a checklist while you are studying. First up, I want to mention that there's stuff from the first test that has just carried throughout the entire semester. Namely the basics of using and converting units, all our descriptions of motion, and force in general. Those things kind of permeate the entire class, and we've been using them throughout the chapters that are on this second test as well. So keep these in mind, even if we didn't have a chapter focused on force within 8 through 20, we still used force in chapters 8 through 20. As for the stuff covered within 8 through 20, first we looked at rotational motion. Just describing rotation as a form of motion separately and also alongside linear motion. Linear motion is straight lines, the stuff we've been doing all semester. Rotational is when things are spinning, and it requires a different set of variables, namely angular displacement for how much something has spun rather than how far forward it has moved, and angular velocity for how quickly it is currently spinning rather than just how quickly in a straight line it is moving. And we also looked at how to convert between linear and angular variables, because there are plenty of objects that spin while moving forward, and the two forms of motion are linked in that case. Namely, if something is rolling, it is both spinning and moving forwards at the same time. The amount that it spins directly ties to the amount it moves forward, and we have formulas that are designed to convert one to the other based on the radius of the object. So for this section, you want to make sure that you can look at the formula sheet and use omega equals delta theta over delta t and these transformation equations in the middle here. Moving on from the basics of rotational motion, we then described centripetal force and acceleration and how that causes orbit. Namely, objects want to move in a straight line, and if you want to make them start turning in a circle, force is required to do that. And what plays the role of that force does just depend on the scenario. Sometimes it is the tension in a rope, and sometimes, like in space, it is gravity. So for this section, recall that any type of force can play the part of centripetal force, and And centripetal force is what will cause an object to start turning in a larger part of a circle. We see this again very specifically with orbit, like the moon spinning around the Earth or the Earth spinning around the sun. Centripetal force is the real one. Centrifugal force is the phenomenon that you feel but isn't really force. So centripetal is the main vocab word you want to use on the test. Related to that, we very recently looked over the universal law of gravitation. Come on. Since gravity is what acts as the centripetal force in space, when I refer to the universal law of gravitation, I am specifically referring to this formula, which is on your formula sheet. One we covered on Eclipse Day. And basically, I want you to be able to, if I tell you the mass of two objects and how far apart they are and ask you for the force of gravity between them, use this formula to be able to do that. Recall that big G is a constant and that is on the formula sheet directly under this formula. You do not have to memorize what uppercase G is. How are you feeling so far? Alright. More rotational stuff. Chapter 8 was pretty long. Torque. Torque is what happens when you exert a force at a radius from a fulcrum. In lab, we used it during the seesaw experiments. Now, if you exert force at a distance away from a pivot point, you create torque, and then the object might start rotating if it is not in equilibrium. On the test, you'll be applying torque to rotational equilibrium problems. Well, a rotational equilibrium problem, which is the fancy term for balance beam questions, like in lab and like we worked a few of these in class as well. So you'd have to be able to look at this type of a situation and balance the torques between both sides to make sure that it remains stable. If you remember from lab, we would hang masses from each side, M1, M2, R1, R2, and there need to be the same amount of torque on each side so that it is level, kind of like, really the same way as if you want things to not accelerate, all the linear forces on them have to add up to 0. So torque and rotational equilibrium are referring to balance beams, seesaws. The last rotational thing that we covered here is rotational momentum. And for this one, in just the interest of you having information, I asked one concept question about this on the actual test, since, again, there's already enough math questions on the thing as it is. What I want you to know about rotational momentum is that if something is spinning, it does want to keep spinning, and its rotational momentum is the measurement of how much it wants to keep spinning. That is to say that its rotational momentum is conserved. If you manipulate some part of that spinning object, it's going to fight you on that, like I did with that wheel with that gyroscope, where once it was spinning, it wouldn't want to tip over. It wants to keep spinning, and that's what the momentum says. What I want you to be able to do with rotational momentum is to look at a situation. I'm going to load up the practice test real quick. Like this, and be able to describe to me what is happening here. So I'll just kind of run through this one real quick with you guys. This is practice test question number 6. A merry-go-round has all of its passengers sitting close to the center axis of rotation, and the whole thing is rotating at constant speed. So all of the people, all of the mass is very strongly concentrated right there in the center. What will happen to the rotational inertia of the merry-go-round if all of these people instead move to the outer edge of the merry-go-round? Yes, that's an answer to a different question. Rotational inertia is the rotational counterpart to mass, basically. If you move the mass further away from the axis of rotation, is this thing easier to make spin or harder to make spin? Harder, exactly. We kind of know this from torque. If the matter is more closely pulled into the axis of rotation, it's easier to make that object spin. But if it's further away, then it's exerting more torque and it's harder to make it spin. Kind of like where you hold a hammer, like what end you hold a hammer from. Dynamic. If all the mass is on this side, it's taking me more effort to hold it, but if all the mass is instead in my hand, it's a lot easier to use the object. So if all the mass, if all the people move to the edge, the whole thing doesn't want to spin as much because now the mass is further away and that affects its rotational inertia, its moment of inertia. If that happens, if all the people move out here, and that's going to increase rotational inertia, the wheel doesn't want to spin as much, what's going to happen to the rotational velocity of this wheel? Slow down, exactly. These people don't exit the ride, they just move to the outer edge, and by doing that, the wheel is now more sluggish. It's still going to keep spinning, it still has momentum that tells it to spin, but it's going to spin a lot slower, even with the same amount of momentum, because by manipulating where the mass is, you've affected how easy it is to make the thing spin. In this particular case, yeah, it didn't give me numbers here. Yeah, if the mass is further away from the axis, the moment of inertia rises, harder to make it spin. Therefore, it would slow down. The reverse would happen if all the mass instead came back into the center. And this is the thing that I did when I held the weights and spun myself in the chair and pulled my limbs in. So, on the checklist, that is what those two blurbs are referring to. And basically, I would present a similar situation as the one in the practice question. I want you to be able to tell me conceptually about that situation. Does that sound fair? All right. That's the end of the rotation stuff. It takes a lot of lines on the list as it happens. Questions, concerns? All right. After that, we moved into our chapters about matter and pressure. This is in reference to 11 through 14. Matter itself was pretty short. In reference to matter, I don't think the states of matter really came. No, never mind. In reference to matter, recall that there are different states of matter that behave in different ways. Namely for this class, solids behave differently to liquids and gases. Liquids and gases are both fluids that have fluid behaviors. Solids don't exhibit those. Also recall how density works. It's mass per volume, and different substances have different fixed densities. And throughout the following concepts, you'll have to utilize volume and surface area, which are not the same thing. So really this section here is just the background information utilized in these sections. And for this list of 5 things, when I say pressure, recall the definition of pressure is force over a surface area. And pressure is created by all kinds of things. For example, fluid pressure at depth, when you are submerged in a fluid, and that does include liquids and gases, that fluid will exert pressure because the weight of the fluid above you is pressing down and squeezing you in on all sides. And so there's a specific formula for fluid pressure at depth that you would need to be able to use on your formula sheet. I might ask you a question like, what is the water pressure this deep down in a pool of water, for example? Buoyant force, related principle. When you throw an object into a fluid, because the pressure increases with depth, there's technically more upward pointing pressure and force on the bottom than there is downward pointing pressure and force from the top. And as a result, the fluid tends to exert a buoyant force upwards, which may or may not counteract gravity downwards. For this section, you want to make sure that you can use the buoyant force formula that's on your formula sheet, identify it and use it, and use it to then identify whether or not something will float. Calculate buoyant force and then use the information to determine if something floats or not. The rules for floating are, it'll float if buoyant force up is counteracted, if gravity is being counteracted by buoyant force, they have to be equal for the object to remain in place. If gravity is bigger than buoyant force, it sinks. If buoyant force is bigger than gravity, it's going to rise until they level out. So, using buoyant force formula, calculate buoyant force, determine if object floats. Additionally, if the substance is more dense than the fluid, it sinks. If it's less dense, it floats. That's another good rule to remember. These two blurbs, Pascal's principle and gas law, very short concept type question. Just want to address what I want you to be able to do with these. Pascal's principle is the one that says that liquids don't compress. You can't squeeze water to make it any smaller. And so instead, when you squeeze water, it just increases the pressure throughout the entire liquid. And that was the type of situation we looked at with the car rising because of the liquid reservoir under the pistons. If you exert pressure on one part of a liquid system, all parts of the liquid system have the same internal pressure now. So that's all this principle here is asking about. Liquids don't compress. Instead, if you exert pressure into a liquid, you pressurize the whole liquid. Separately from that, gas law says that you can compress a gas. If you squeeze a gas, it will get smaller. If you double the pressure, it will shrink to half the size, half the volume. So that is all I'm asking for these two blurbs. You can't compress liquid, instead you just pressurize it. You can compress gas, in which case, double the pressure, halve the volume, halve the pressure, double the volume. Is that okay? All right. Then, for the last couple things that we've been covering the past weeks in relation to waves, these take up more space than I realized. Waves, want to be able to recognize and measure the basic aspects of a wave. Amplitude is, again, the size of the wave, which is size from baseline, not the whole thing, but from baseline to either top or bottom. Crests and troughs are the top and bottom points of the wave. Period of oscillation and frequency are inverses. Period is how often, how long it takes one wave. Frequency is how many waves per second. They are inverses. And wavelength is physical length of a wave, different from amplitude. Those are those are the things about waves that we measure to understand them, and then they are used throughout later principles. For instance, wave speed. All waves have a speed because they are traveling energy. This is really in reference to this formula. Wave speed equals frequency times wavelength. I want you to note again that the speed is usually constant for a given type of wave. If you're looking at a sound wave, different frequencies of sound would have the same velocity, and changing the frequency would only change the corresponding wavelength. So that's the main thing I want you to remember about this formula. If it's different sounds, you're probably going to be plugging in the same speed of sound for each one and finding a different frequency wavelength pairing. So the wave speed blurb is in reference to this fact about this formula. The Doppler effect was the concept that says the frequency of a wave perceived will change based on if you or the source of the wave is moving. This is when we talked about, trains and ambulances passing by and you hear that very specific meow sound. That's again the Doppler effect. If two things are moving closer together, the waves that they make and perceive will be higher pitched than they're supposed to be. If things are moving apart, the waves that they make or observe will be lower frequency than they're supposed to be. That's the main thing I want you to remember about that one. Same is true for echolocating bats. If a bat emits sound and gets back a higher frequency, it's because it bounced off of something moving towards the bat. If the bat emits a frequency and hears back a lower one, it's because whatever the wave bounced off of is moving away from the bat. That's its main application for animals and sonar. Wave types, there's two ways that we categorize waves, and each of those two waves has two options, transverse and longitudinal. Transverse for if it's vibrating perpendicular to travel, longitudinal for if it is vibrating parallel to travel. Sound is longitudinal, light is transverse. That's the main thing I want you to be able to apply it to. Similarly, we categorize waves by what they're physically made of. If a wave is mechanical, then it requires a physical medium. If it's electromagnetic, it doesn't, because it's literally made out of electromagnetism. Sound is mechanical, light is electromagnetic. So really I want you to look at this list of terms and be able to point out sound, longitudinal mechanical, light, transverse electromagnetic. So just vocab word application. And lastly, we spent today looking at just some sound specifics. Speed of sound, it's usually going to be about 343 meters per second. I would provide you that number, but I want you to note that that number does change if the medium the sound is played through changes. 343 is the speed of sound in room temperature air. If the air is cold, that slows down. If the air is hot, that speeds up. Bless you. If the sound is played through water, it gets even faster. If that sound is played through earth, that is the fastest. So you manipulate sound speed by manipulating the material that the sound is playing through. You do not manipulate sound speed, bless you, by changing frequency or volume. Those have no effect on speed of sound. Then, in reference to speed of sound, just note that technically it's still a velocity, and therefore you can still use delta x over delta t to track the distance and time that sound takes to travel. In reference to the question where we determine how far the thunder has to travel from the lightning bolt to our ears based on the time delay, or also the echo question with a bat just listening for its own echolocation. Well, I guess we did a cave, but bats apply that technique on purpose. That sort of thing. Note though, in that type of question, if you are looking at an echo, the time it takes to hear the echo is double of the time it took for the wave to actually hit the target and then come back. So if it takes about 10 seconds to hear its own echo, how far away in seconds is the target? 5, very good. And that's everything. There's a lot of different things on this list. The second half of the course is the half that has the most variety in concept. But it is now a finite list. If it's not here, it's not on the practice test. And all of these concepts are used on the practice test in similar ways to the actual test. Note though, when you are working on the practice test, I always make it longer and more difficult, at least more arbitrary than the actual test, because I'd rather you make your mistakes on this than on the real thing, because I'm gonna post an answer key for this. I want you to learn something from this and then get better on the actual thing. For example, practice test has 16 questions on it, real thing has 13. Real things questions tend to be a bit shorter. Practice test has mostly multi-parters and a few extra concept questions on the front just to make sure that all these vocab words make sense to you. So, as you're studying, use the checklist, make sure everything on it feels comfortable to you. Look over your formula sheet. As a reminder, you should bring your formula sheet to the test. If you don't have one of your own, I will have a pile of them at the front of the room. You will have a formula sheet. You should also bring your own calculator. And work on the homeworks and on the practice test. Answer key for the practice test will be posted this afternoon. How you guys feel? All right. As a reminder, we will use we will use lecture next Monday and Wednesday as more review days. So while you're working on all your study stuff, you should bring, you can email me questions at any point, but you should also make sure to bring questions to Monday and Wednesday if there's anything you want to talk about or work on in the room with me and other people. That is what lecture Monday and Wednesday will be. Friday next week, my goal is to have the test graded and handed back to you so that we can spend the last week of the semester talking a bit about electricity and then exam review. Does all that sound good? All right. Well, with that, that is all the material that I absolutely wanted to cover today. And so, got about 15 or so minutes before the class is officially supposed to end. I'll put it to a vote. I could talk a bit about some facts about light waves that I enjoy talking about because I'm a big old nerd, or we can break for the weekend. It's up to you guys. If you want to head on out, you can. If you have questions or you just want to hear me ramble about light physics and optics, you can stick around if you want to. But that's everything we needed to get through today. Let me know if you have any questions while studying. And please have a wonderful day and weekend. First of all, this calculation is... No, oh, that's fine. Yeah. Here the problem is, I just don't think you divided right, because this, you're supposed to divide both sides by R, therefore the answer should be really
And it
because this answer, once you find it, will be like this. That answer will be units of radians per second. That again tells you how quick it is. You can convert that into units of rotations per second. And to do that, you just need to remember that one rotation is 2 pi radians. Just use that as a conversion to change the unit over. And once you have rotations per second, you could figure out seconds per rotation and then days per rotation. Yeah, and this is the conversion you use as well.
Was that number 5B?
1F.
Okay, never mind. I usually go over 5B on practice.
Can do. Thank you.
So how do I get it from radians to rotations? Do this? Like from
Yeah.
this to this?
This isn't the exact answer.
Okay.
Just to kind of show what I would be expecting. Some number of radians per second. The seconds part is fine, but you want to replace radians with rotations.
Okay,
And so I would divide by 2 pi rad to replace it with 1 rot. And that would cancel out units of rotation, of radians, leaving us with rotations per second. And so whatever number you get for E, again, this is the right
yeah.
tail end of it, I just forget what's on the front. You'd want to take that and divide it by 2 pi, and that would get it into rotations per second.
Okay,
Once you have rotations per second, you can just take the whole number, divide it by 1, and get seconds per rotation.
okay,
The number of seconds it takes the moon to make 1 trip.
perfect, okay. Thank you so much.
You're welcome.
Thank you.
You're welcome.
Count on number 5.
Mm-hmm.
I think I corrected it right. I think it was